Welcome back everyone. In this episode we're going to continue our exploration of networking, and specifically we're going to look at the options for how you might network the very first arcade game. So let's get started. This is Pong, released by Atari in 1972. It's a two-player game similar to tennis. Each player controls a bat using an analog control knob. It's actually based on an even earlier system called Brown Box, invented by Ralph Baer in 1967. Here he is with Bill Harrison playing in 1969. My introduction to Pong was via one of these Binatone consoles, released in 1978. It should plug into the aerial socket on your TV set. It claimed to play 4 different games, but really they were all just Pong at heart. I think it's high time that Pong was brought into the 21st century as a two-player network game. How hard can that be? So let's think through the problem of how we network the game of Pong from first principles. We've got 2 computers, and each of them has a player. Now, the first question we should ask is, where are we actually going to do the modelling of the game? I mean, the interactions between the bat and the ball and how fast the ball moves and things like that. Where are we going to do that? And it turns out there's actually not really a terribly simple answer to that question. I mean, we could put the model over here. And that means that both of the games are going to be interacting with the same model. And that has a big advantage in that the game is always going to be consistent. But it has a big disadvantage for player 2, because they're the other side of the network, and the network might have a couple of 100 milliseconds of latency, and a couple of 100 milliseconds of latency is going to be the difference between you missing the ball and hitting the ball. So that would put player 2 at a big disadvantage. So this is not going to be the way to do it. It doesn't work if we try to do that. So what else can we do? Well, we could introduce a server. And the server runs the model. And actually quite a few network games actually do this. But there's still a disadvantage to it, which is that both of the games now have to interact with the model running on the server. So again, we've got a completely consistent game. But this only really works if the delay from each of the players to the server is the same. If one person has a pretty poor network connection, the other person has a pretty good network connection, then this player is going to have a big advantage, and we don't really want that. We'd like it to be an equal game. And there's also the problem that actually the server might not be in the middle. The server might turn out to be pretty well located for one player and not very well located for the other player, and that gives the same degree of unfairness. So if we can't do any of that, well, what are we going to do? We're going to have to actually distribute the model. We're going to have to place part of the model over here and part of the model over here. And then they're going to have to talk to each other so that this stays consistent. And that means that the problem is not quite as simple as maybe we first thought it was. So let's break down into pieces what we mean by distributing the model. First of all, let's consider the 2 bats. Now, the reaction times in terms of manipulating a bat need to be pretty good. So really, you want, as soon as you move the bat, to see the bat move. And that pretty much dictates that each user has to control their position of their local bat directly. We don't want to have that go over the network at all. And so each user will control their own local bat. They'll be able to see their bat on their screen. No problem, that's very easy. Now, of course, we also want the users to be able to see each other's bats as well. And so that's fairly easy to do as well. Once he's updated his bat position, we'll send a bat update message across the network, and so that she can see the position of his bat, remote bat. And as she doesn't directly interact with the remote bat, then that doesn't really matter if that's fractionally delayed. And vice versa, we'll send her bat update message across the network and update his concept of the remote bat. So that's fine. In this case, we've got a pretty simple distributed model. Both of the bats are moved locally. Both of them tell the other side where the bat currently is so that it can be displayed remotely, and there's no problem. But that's because they don't directly interact with each other. But they do interact with the ball. So where are we going to model the ball? Now, it's pretty clear that when the ball is speeding towards your bat, it's really important that you can see exactly where the ball is, with no delay. And so what this means is that when the ball is speeding to your bat, it's pretty clear that the ball's position must be being modelled on your computer. Otherwise, if it's being modelled on the other computer at that point, there'll be too much delay and likely you can miss the ball. And similarly, when the ball's speeding towards the other person's bat, you really want it to be modelled on their computer. And so this gives us an idea for how we might split the processing. And we're going to have to distribute the processing in some manner if this game's going to be fair. So simple sort of idea for how we might make this work is that when the ball's on your side of the court and it's speeding towards your bat, it's modelled on your computer. And then when it goes onto their side of the board, it starts to be modelled on their computer. And therefore, when it's speeding towards their bat, or missing their bat, then it's been modelled on their computer. And then both sides get a low latency interaction with the ball. So that's our first hypothesis as to how to build this. So let's think about how that might actually work. Well, I've implemented this distributed ball model, and let's just say it doesn't quite work as expected. Yeah, let me show you. It's fine, and then it stops. Okay, let's do that again. Runs fine, bounces, and stops. So what's going on here? Well, think about it from the point of view of the ball when it's in my side. When the ball's in at my side, I'm modelling the ball, I'm modelling its motion, and I'm telling the other side where the ball is. Now, as the ball approaches the centre line, I'm still telling the other side where the ball is. But then the ball crosses the centre line, and now it's not my problem anymore. So the other side should pick up modelling the ball and deal with it. But now if you think of it from the point of view of the other side, they saw the ball approaching the centre line, and they saw it just before the centre line, and they didn't get a message that it crossed the centre line. And of course they didn't get a message across the centre line because I never sent one, because it wasn't my problem once it had crossed the centre line. So from their point of view, the ball never got there, and so it's still my problem. And from my point of view, the ball has already left, and it's their problem. And so we've got a deadlock here. Can't go any further because each side thinks the other side is responsible for the ball. So maybe we need to rethink that strategy just a little. Okay, so I've made one small change, which should fix that problem. All I do is I keep sending the position of the ball until it's gone over into the other side of the court, and then I send one more message once it's in the other side of the court, and that will be enough that the other player knows the ball is now their problem, and we won't have this kind of deadlock. So let's see how that works. And it's all working. So our distributed ball model is all working just fine. So what next? In the previous video, we used a protocol called TCP for our chat application. And we use TCP because it reliably delivers data across the internet. But how does TCP do that? And is it still the right choice for our Pong game? This is a simulation of two computers trying to send to two other computers. Computer number 1, the yellow, is trying to send to computer number 2, and in a little while, computer number 3 will try and send to computer number 4. Now, computer number 1 is sending a large file, and that file is broken up into packets of data to be sent across the network. Now, the problem that computer number 1 faces is it doesn't know how fast it should send. In this particular case, this is the slowest link in the network. So in order to find out how fast to send, it just keeps increasing the rate that it sends. And eventually this starts to build up a queue in the network. And as it keeps increasing, eventually it overflows the queue and a whole bunch of packets are lost. So it got it wrong. It sent too fast. Now, how does it know that it got it wrong? Well, what we're seeing is data packets that are going in this direction. And we're also seeing these little tiny packets that are going in this direction. And these are acknowledgement packets, or ACKs. So for every data packet that arrives at computer number 2, an ACK is sent back. And so what computer number 1 can do is it can see from the fact that some of the packets were not acknowledged that it sent too fast and some packets got lost. So when that happens, it does two things. The first thing it does is to slow down, and then it will speed back up again slowly. And when it does that, it can roughly match the amount of data it has to send to the capacity of the network. So now it's sending at roughly the right rate for the link. We've got a bit of a queue here, but it's not too bad. And the second thing it can do using those ACKs is to find out that data was missing, and because TCP is a reliable protocol, once it discovers the data is missing, because the ACK didn't arrive, it will resend that data. So computer number 1 will hold on to all of the data until it just gets the ACK back from computer number 2, and then it will resend anything that's missing. Anything does get there, then it's fine, it can discard that. Now, computer number 3 just started up here, and it got a little bit unlucky. One of its early packets got lost because it unfortunately was sharing the network with the yellow traffic. That's the nature of the internet. Often you're sharing the network with other traffic. And so now it's going to slowly increase the rate that it sends and until it starts to actually get some fair share of the network. But it might take a little bit of time because it got a bit unlucky at the start. So this is the nature of the problem that you face when you're writing networking code. You don't have the network to yourself, and you're going to have to cope with whatever the other traffic is doing at the same time. And that other traffic, even if your traffic is well behaved, may cause queues to build up, and it may cause packet loss. So TCP then is solving two main problems. The first problem it's solving is one of reliability. And it does that by nature of sending packets, getting acknowledgements back, and when it fails to get acknowledgements, it will resend the data across the network. The second problem it's solving is basically how fast to send. And it does that by probing, by increasing the amount of data it sends until some data gets lost, and then it will slow down and increase again. So in solving these two problems, we've managed to get the network to go more or less as fast as it's capable of and make it reliable. But there's a price you pay for that. And the price you pay for that is that sometimes packets are going to be lost. And so they won't arrive on the first try. It'll take a few acknowledgement packets coming back across the network to computer number 1 here to tell it that packets were lost. And then it will resend. And so there'll be a delay before that data gets there. And because TCP delivers everything in the original order, it will not only delay that packet of data, but it will delay anything else that arrived here after the missing one until the hole is filled, and then it can release the data to the application. So that's one source of delay. But the second source of delay is how fast should we send? If TCP concludes that it's sending too fast, faster than the application is trying to send, then data will be queued at the sending computer here until TCP decides it's time for it to be sent. And so that's a second source of delay. And between these two sources of delay, we get quite unpredictable delay across the network. It's usually not too bad if the network's working quite well, but sometimes it can be not negligible. So that's the price we pay for using TCP. It's nice and reliable, the data will get there, but when it gets there, it's determined by any retransmissions that happen and by TCP trying to be nice to the network and sending at an appropriate rate. So if TCP might add a bit too much delay for our game, what's the alternative? Well, the alternative is UDP, or the User Datagram Protocol. And so UDP is really simple. Whereas TCP does all of this retransmission and trying to figure out how fast to send and things like that, UDP does none of that. With UDP, when you call send on a UDP socket, it just sends. That's it. Nothing else. It just sends. It doesn't do any retransmission. It doesn't do any acknowledgements. It doesn't do any rate control stuff. It just sends. It means the packet goes out of your computer when you say send. And that means that you've got to think carefully about how you use it, because you've got to build your protocol on top of this to take advantage of its advantages and disadvantages, let's say. Now, suppose we're modeling the ball and it's heading off in that sort of direction. Okay, so we've got to tell the other side where the ball is. So we're going to send an update message. So that's message number 1. And then shortly afterwards, we're going to send another update message. Message number 2. And shortly after that, we'll send another update message. Message number 3. Now, we're probably sending these pretty often. Maybe as often as once for every frame of animation. So maybe, let's say, 30 times a second. And it can take a little while for those messages to get across the network. But that's okay. Message number 1 travels across the network, and when it gets to the other side, it's going to go and update the position of the ball at the other side. It's there. Okay, so what happens next? Well, message number 2 travels across the network, following shortly behind message number 1. But it gets unlucky, and it gets lost in the middle of the network. Shortly after that, message number 3 comes flying across the network and arrives at the receiver. So what happens next? Well, that depends on whether we're using TCP or UDP. If we're using TCP, then message number 1 arrived and message number 3 arrived. But because TCP has to reliably deliver the messages in order to your application, it can't send message number 3 up to the application to update the position. So it's going to get stored in a buffer and it's going to sit there waiting. In the meantime, the acknowledgement of message number 3 goes back across the network, and usually a few packets later, a retransmission of message number 2 will finally arrive, coming across the network. Message number 2 arrives, and that means that we can now send message number 2's update here to update the position of the ball. And finally, we can immediately after that send message number 3's update to update the position of the ball. But from the application's point of view, these ones arrive right one after another, and so there really wasn't any need for message number 2. It didn't serve any purpose, because we immediately discarded its position and replaced it with message number 3. So TCP's retransmission didn't really serve any purpose for us here. So what would have happened with UDP? So with UDP, message number 1 arrives, and it updates the position of the ball as before. Message number 2 doesn't arrive. But message number 3 arrives 2/30ths of a second later and is immediately passed up to the application, where it can update the position of the ball to where it was at that position, and there's no delay on message number 3, it just updates as soon as it can. So the issue here is that if we retransmit message number 2, it serves no purpose, because by the time it arrives, it's too late for it to actually be useful. We might as well just not care. We only care the fact that there's a message right after it. Now, this works great so long as we keep sending update messages. If we're sending update messages really frequently, then losing one of them doesn't matter, because it will immediately be supplanted by the next one, which provides the next update, and there's no point in waiting for a retransmission. Where it doesn't work quite so well is where you need something that's actually reliable. So in the Pong game, there isn't really anything that needs reliability in here. We can just continuously update the positions of the bats. We can continually update the position of the ball. Maybe you need reliability when the ball goes off of the field, but in reality, we probably don't really even need reliability for that. So long as it goes off the field, the model responsible for it going off the field notices and puts the ball back into play. So we don't need any reliability beyond just sending messages for the Pong game. It's not quite the same for the Pac-Man game. In the Pac-Man game, there are definitely some messages that need to get there reliably, but not all of them. And so for that game, you're going to need to think through which things actually need to be reliable and which things are more like the ball position in Pong, which don't need to be reliable, we just need to send them often. So I modified my Pong game to use UDP instead of TCP, and it was pretty easy and it works just fine. So then I thought, well, actually, maybe it's working fine just because I'm only using it locally. I mean, if I use it locally just to test on my own machine, there's pretty much never going to be any packet loss. And so I thought I'd probably better test it in a slightly more rigorous environment. And so now I'm testing it over a network that emulates 10% packet loss. And it doesn't quite work fine anymore. So let's see what happens. Now it's working okay. And then it stops. Try again. It's working just fine. And then it stops. And so sometimes it crosses the middle and sometimes it doesn't. So what happened there? Well, we were transmitting the ball position, and we kept transmitting the ball position. And remember, our reliability mechanism says we transmit the ball position once it gets into the other side. And so the other side received those ball positions, but we got unlucky. The packet that sent that one got lost, and so it was never received over here. Now, on this side, we think the responsibility for modelling the ball belongs to the far side, and on this side, we think the responsibility for modelling the ball still is on the other side, and so we're back in the same deadlock that we had before. So how are we going to resolve this? Well, it's actually fairly simple. What we do is we just keep sending the ball position until the other side receives the ball position over here and concludes it's its job to update the ball position. And so it's now going to update the ball position and send it back. And as soon as we receive this one from the other side, we now know that the other side is modelling the ball. And so we can stop now. We don't need to keep sending because the other side now has the ball. And so what we've got here is essentially a handshake. This side keeps sending the ball position until it gets an acknowledgement back that the other side has received the ball position. Now, this acknowledgement isn't an explicit acknowledgement, it's just a ball position message back from the other side. But that's enough to make sure that we know for sure that the other side has got the information that they needed to get. And that's all we need to do to make this reliable. So I've implemented that idea, and this is it running. This is with 50% packet loss. We're losing half of the packets. And yeah, it's a little bit glitchy when you only get half of the messages, but it's still working and it's working reliably. So I think we've solved that problem. Now, what next? Well, the other effect of networks is not just loss, but also delay. And testing it out on my local computer here, I'm not really seeing any significant delay. So I think I'd better test it with some emulated network delay. So we can see the effects of latency. I'm introducing a simple emulation of network delay. So I'm still going to be playing my computer against itself, but I'm emulating the same thing that would happen if the network path had about 250 milliseconds delay going out there. So that'd be around a half second going there and back. Now for the internet, that's a fairly large delay, but it's definitely something that you could see in the real world. So should we see what effect that has on the game? Okay, so the yellow bat is the local one, and the grey bat is the remote one. And you can see that the ball is just fine as it comes from them to us, but as it goes from us, it glitched, you see? Coming from us to them, it goes over, and then it glitches back to the midline. Coming from them to us, no problem. Every time from us to them, it glitches back to the midline. So why do we get that glitch in the ball's position as it crosses the middle of the screen? Well, it's entirely due to the delay in the network. And so, for the sake of illustration, I'm going to imagine that the delay is significantly larger. And so, what happens is the ball is being sent from, let's say, right to left here. And we send the ball position, and we send the ball position, and we send the ball position, and we send the ball position. And these messages are all in flight. They haven't got there yet. Eventually, the first message gets there. But we're at least 4 messages behind, just because of the delay in getting things across the network. So now we send the next one, and that one gets there. We send the next one, and that one gets there. We send the next one, and that one gets there. And because of our reliability mechanism, we're still sending because we haven't heard back yet. We send the next one, and that one gets there. We send the next one, and that one gets there. Okay, so now the other side knows that they need to send back. So they send back, but it hasn't arrived yet. So now next one goes through. And they send the next one. It hasn't arrived yet. Next one goes through. Send the next one. And finally, this one arrives. Bloop. And so the ball went all the way over here, and then it glitched back to there and then started moving again. And so that's the effect of latency in this. There's always going to be some discontinuity somewhere, and putting that discontinuity right in the middle of the screen puts it right where it's most visible. It also means that we don't get to actually track the whole ball visually all the way towards us, and that's probably a bad thing too. So we can't get rid of that latency. That's just inherently part of the problem. But what can we do? Can we do something different in terms of who models the ball? Well, yeah, splitting the screen in the middle seemed like an obvious thing to do, but actually it's probably not the best thing to do. It might be better if the ball is modeled when it's heading towards us. So if the ball is heading towards the yellow bat here, it's modeled by the yellow bat all the way from the point where it sees it turn around. And then we're still going to transmit after it's turned around, because we need to do that in order to inform the pink side that the ball's, but by the time they finally get the message that the ball has turned around, then they're going to think it's back here. So it will glitch backwards, but it glitched backwards just after it turns around at the bat. And that's probably the best place to hide any glitch. And then we can have the pink side model the ball the whole rest of the way. So anytime the ball's heading towards you, you model the ball. Anytime the ball's heading away from you, the other side models the ball. But you keep modeling it after it bounces until the other side gets a message to you, and then you know that they know what's going on. And that way we do the best job to hide any glitches right at the point when the ball turns around, and it shouldn't be terribly noticeable there. But as I say, there's always going to be some discontinuity between the two sides. Now, if you really care to try to hide that discontinuity, then when it glitches, you could potentially slowly speed the ball up so that it actually reaches the correct position. But that's a little bit beyond what I want to do today. I've implemented those changes too, and well, you can see the results. This is emulating 10% packet loss and 100 milliseconds of network delay. So that's actually a network that's pretty poor. 10% packet loss is about as high as you're likely to see in the real world on a network that still functions. And 100 milliseconds delay is actually fairly high for this. It's certainly very high for playing an interactive game like this over. And well, what we see if we watch it as it comes towards the yellow bat, towards us, it's nice and smooth. As it goes away towards the far side, it's a bit glitchy. And of course, this is because as it comes towards us, it's being modeled on our machine. And as it goes towards them, it's being modeled on their machine. And of course, we only really care about it moving smoothly when it's coming towards us, because we're trying to get the hand-eye coordination right when it's heading towards us. So this is actually a pretty reasonable solution to this problem. Now, in general, when you're thinking about designing networked software, a classic beginner's mistake is to ignore the effects of latency. You really can't ignore it most of the time. You have to figure out what the effects are going to be. And also, if you're using an unreliable protocol like UDP, you absolutely have to consider the effects of packet loss. You can't ignore that either. You have to design it into your algorithms. But with the right algorithms, actually, we can make things work pretty well, despite this fairly broken emulated network that I've got here. I think we finally understand our game and our protocol well enough that we could actually think about writing a specification for the protocol. So the first thing to decide realistically is whether we're going to use UDP or TCP for this, because this actually influences quite a lot of the rest of the semantics. So I'm going to use UDP for this particular one. It seems like it's the best fit for the particular game. Now, the next thing we need to think about in terms of semantics is what messages are actually sent. And to decide that, we need to know what does the receiver need, what information do they need, and when do they need it. So for the main part of the game, there's really only two pieces of information we need to send. The first piece of information is, where is our bat? And for that, all we really need to send is a y coordinate. And the second piece of information we need to send is a ball, when we're modeling it, and that's going to be an x and a y coordinate. Okay, so that's what information we need to send, but when do we send it? For the bat, we're going to send it as often as we can, which is basically going to be every frame. So likely something like 30 frames per second. For the ball, we're also going to send it every frame, but we don't actually send it every frame. We only send it when we're modeling the ball. There's no point in sending it the rest of the time. The message won't be used. So that's the thing. We'll send the ball as often as we can, every frame of the animation, but only when we are modeling the ball. Now, that leads to the question of, we need to define when we should be modeling the ball. Otherwise, you can have a deadlock. So we're going to define that we should be modeling the ball from the first moment when we see the ball heading towards us. So we'll receive an update message from the other side, and as soon as we see the ball heading towards us, that's when we start to model the ball. And we continue to model the ball all the way until it either goes off our side, in which case we'll restart, or it bounces off our bat and starts to head towards the opponent. But we won't stop modeling it quite then. We'll stop modeling the ball when the ball is heading away from us and we receive the first message back from the other side, also saying that it's heading away from us. At that point, we know the other side knows, okay, so we've done that handshake, we're good, it's not going to deadlock. Now, what else? We've said we're sending coordinates. Are we just going to send coordinates? We need to make a decision on this. We could just send the x and y positions, but we could also send a velocity. And if we choose to put a velocity into the protocol, it's because what we want is for the receiver of the messages to be able to animate in the motion of the bat or the motion of the ball for a short period of time if some messages get lost. And so as we're using UDP, it probably makes some sense to put a velocity in there in addition to the bare minimum, which is the positions. Now, what do the coordinates actually mean? We've got x, y coordinates, but what do they mean? Well, they're not defined yet. So there's two parts to this. The first part is, what range are they in? And so we should just specify that. And for this particular game, it's probably reasonable to specify the coordinates are in something like a range of 0 to 1024 in both directions. That gives us enough precision, and 1024 neatly fits into 10 bits, which is nice for a binary encoding. The second thing we need to determine is what the coordinate system is. Now, not what the range is, but what the coordinate system actually is, as in where is the origin? And this is slightly complicated by the fact that it's pretty natural that when you start up the game, you are always at, say, the left-hand end. But that means that for one of the two players, the whole coordinate system has to be flipped. And so in order to decide what the coordinate system is, we're actually going to have to decide who is player one and who is player two. And we will specify that the coordinate system, the origin of the coordinate system, is at the top left corner of player one's screen and counts across and down. And therefore for player two, it's all reversed and the origin of the coordinate system is at the bottom right of their screen. If you don't specify these details, there are going to be misunderstandings as to what the numbers actually mean. We have to specify what they mean. Okay, so that's fine. We've got range of 0 to 1024 and we know where the origin is, we know which direction things go, so that's reasonably unambiguous. We've still got to decide who is player one and who is player two. So we're going to need some form of tie break to decide that. It doesn't matter which way round they are. It's absolutely fine for either of them to be player one or either of them to be player two, but we need to decide. So the second thing we need to do is to somehow synchronize the start of the game. Especially as we're using UDP, so there isn't really a connection to be started up, we're just sending packets. So we'll need some form of initialization messages that go backwards and forwards in order to synchronize the start of the game. And a pretty simple way to choose who is player 1 and who is player 2 is for each side to pick a random number in a big range, say 64 bits, and whoever picks the lower one is player 1. The chances of them actually colliding are effectively 0. Nobody's going to play the game that many times for a collision to actually happen, so that's probably sufficient. So we'll add some initialization messages. They'll include a big random number, and each person sends them to the other. When they keep sending until they get initialization back from the other side, and then that's basically a pretty simple way to get the game started. And include a random number. We use that to choose who is player 1 and who is player 2. So I think that's pretty much all of the semantics of this game. The only things we need to do in terms of the protocol anyway. Now, in addition to that, a specification will include the syntax of the messages. It will include which information goes in which packets, how is that encoded, is it a binary encoding, is it a text encoding, if it's a binary encoding, how big are the fields, if it's a text encoding, what's the grammar, and we need to specify that information too. And then there's one final thing, is that we probably don't want the protocol to be too chatty, because for a bat message, we're really only sending one or maybe two pieces of information, the y coordinate and the velocity. And so those are realistically only going to take us about 4 bytes, but we have to factor in the fact that the IP header and the UDP header are going to take 32 bytes. So we have a 4-byte payload and quite a big header to stick on the front. So if we can put more than one of these pieces of information into the same packet, that would probably be a good idea too. And we can, because we're always sending bat messages, we can always make sure that the ball messages just go into the same packet as the bat messages. And so we would specify that that happens too. And that will give us a slightly more efficient protocol. It roughly halves the data rate at the peak. And so that's definitely worth doing. Okay, so that's pretty much all the things we need to put into a specification. I'm going to put some sample specifications on the course GitHub site so that you can look at how those might be written. But the most important thing is not how they're written, but what actually goes in them, what's needed to be specified in order to actually understand the nature of the protocol. So that's just about it for distributed Pong. Now, I have to admit, it's not the most exciting game in the world, but it does illustrate a whole bunch of points really quite nicely, and so I think it's actually worthwhile thinking about. Anyway, see you next time.